So now we want to think about which of these two approximations is more accurate. So in the pictures we can kind of compare how these two approximations were calculated. So when we did the trapezoidal rule, we approximated using these trapezoids, which you can see here actually do a pretty good job of approximating the area under the curve. Perhaps over here where the curve is clearly underneath the top of the trapezoid, you can see that there is a tiny error there between the top of the trapezoid and the curve that goes underneath it, but as the curve flattens out, the trapezoids become closer and closer, so the error perhaps is getting less as those trapezoids go along a flatter portion of the curve. So here it appears that the error is perhaps not that bad. What about over here when I look at midpoint? Well, in this case, you've got part of the rectangle that goes under the curve, so it's under approximating on half of it, but then the other part of it sticks out above the curve, so then it's over approximating on the other half. But what we can imagine is that this is actually going to be pretty okay in general, because the amount that it's under approximating by can be sort of balanced out by the amount that it's over approximating by. And so my guess is that because of that, it will tend to be a better approximation. Whereas over here, even though it looks like it fits the curve better, notice that it doesn't have that property where it balances out by over and under approximating with each rectangle. Here, it's always going to be over approximating. Each of these trapezoids is always going to be above the curve. So when you sum it up among all the rectangles, or in this case all the trapezoids, that error will accumulate. So even though this one appears to be a very good approximation, it turns out that the midpoint rule will actually be a more accurate approximation. So let's actually see how big of an error we get when we do this approximation. So to get the actual value of the integral, let's actually work it out. This one we can work out using what we know about the integral of 1 over x. Remember, that's ln of x, and then we'll evaluate that from 1 to 2. So this will equal to ln of 2 minus ln of 1. ln of 1 is 0, so this is just equal to ln of 2. So in fact, the actual value of this integral is what ln of 2 is. So let's use our calculator there to get the most accurate value for ln of 2. Which here on my calculator, I get something around 0.6931471,806. And if you remember when we did the trapezoidal rule for T5, I got something around 0.6956349,206. So to figure out what kind of error was there, we'll take the difference between the two. So we'll take T5 minus the actual value, ln of 2. And this will tell us the error, we're calling it ET, in that approximation. Okay, so here I'm going to subtract those two values and see what we get. In this case, I get something around 0.00248,774. Okay. So that's telling us essentially the error is telling us how much the actual value differs from our approximated value. Okay. How about our midpoint approximation when we did M5? I got a value of around 0.6919078857. 57. Okay. Okay, so to get the error in this approximation, I'll subtract what we got for M5 minus the value, the actual value, ln of 2. Okay, so if I subtract these two values, what do we get? In this case, I get something around negative 0.0012392949. Okay. Even though this one was negative, notice that that's really just telling us that it was an under approximation. It was underneath the actual value. But in absolute value, if I'm looking at, say, what we're calling the absolute error, put these in absolute values, comparing the absolute values here, then in absolute values, if I were to get rid of this minus sign, this one has a smaller error. So here it appears that midpoint is more accurate. Since it has a smaller error, that tells us that the actual value is closer to the approximation we got with the midpoint rule. Okay, and we can see that it's actually almost about half of the error that we got with the trapezoidal rule. Okay. And I think a big part of that was kind of what we observed in our picture, that the midpoint tends to both over and under approximate with each rectangle, whereas the trapezoid will almost always go one direction. In this case, it was over approximating. Here, the midpoint tends to balance out a little better. And here's to kind of look at a variety of different approximations to see roughly how these different approximations compare. So definitely the trapezoid and midpoint rules are going to be much more accurate than the left or the right endpoint rules. So computing the same integral with left endpoints, right endpoints, trapezoidal, and midpoint rule, we're also looking at different number of rectangles. So clearly what happens is that as we increase the number of rectangles, we get a more accurate approximation. And it looks like here that if I had n equals 20 rectangles, that the left and the right endpoint rules are still not very accurate compared to the trapezoid and midpoints. And to see the actual errors here, even with 20 rectangles, the left and the right endpoints had pretty big errors, especially compared with the trapezoid and midpoint rules, where the errors were very small. And we see that among these different rules, these different approximation rules, the midpoint has the smallest error of all of them. Okay? So to get the most accurate approximation using midpoint is your best bet. In fact, with just n equals 5 subintervals, our midpoint rule had a much more accurate approximation than using 20 rectangles with the left or the right endpoints. Right? It was still more accurate to use midpoints with only 5 rectangles. So in a way, that's going to save you a lot of computational energy. So one thing we can observe is that among all these methods, as we increase the value of n, the approximations will get more accurate. Essentially, we're filling in the gaps that are made with each of those approximating rectangles when we add more rectangles. So they become narrower and they fill in the gaps and we get a better approximation. But, of course, this is a difficult thing to do computationally. The larger n is, the more computation we have to do to compute the approximation. So that's the trade-off. We noticed that comparing the errors in the left and the right endpoint approximations, they were essentially opposite in sign, but were pretty comparable in value, in absolute value. and they tended to decrease by a factor of 2 roughly when we double the value of n. With the trapezoidal and midpoint rules, they were much more accurate than either the left or right endpoint approximations. And we noticed that the errors in the trapezoidal and midpoint rules were opposite in sign, and they appeared to decrease by a factor of about 4 when we double the value of n. So here it was much more effective to get a much more accurate approximation to use trapezoidal or midpoint rules. When we increased the number of rectangles, it had a much better result. And the size of the error in the midpoint rule is about half the size of the error in the trapezoidal rule. So the midpoint rule perhaps was twice as effective. And here's a rule that can help you approximate how accurate our midpoint or trapezoidal rule approximations will be. So these are going to give us bounds on the error. So we're starting by finding some value of k such that the second derivative of our function is less than or equal to k for all x in our interval a to b. And here et and em are the errors in the trapezoidal and midpoint rules. So this will give us an error bound on the trapezoidal error. So it's less than or equal to an absolute value k times b minus a cubed over 12n squared. Compared with, for the midpoint rule, it's k times b minus a cubed over 24n squared. So you notice that it's about half. It's half of what it is for the trapezoid.